In this video, I'm going to be talking about partial fraction integration, which is going to be a technique we can use to take difficult-looking integrals and make them much easier. And it's going to rely on an algebra technique that hopefully you studied in a pre-calculus or an algebra 2 course somewhere along the line. So to start the discussion, I'm going to talk about 1/2 plus 2/3. And we know that we can't add 1/2 plus 2/3 to say it's 3/5. That's just not how it works, right? Then if that was the case, if we added 1/2 to 1/2, we'd have 2/4, and 1/2 plus 1/2 is not 2/4. We know this. Okay, so we need a common denominator, right? And what we're going to do, basically, to get the common denominator is we'll, multiply by some clever form of 1 that will help us. So 1/2, I want to multiply by 3/3 to get that common denominator of 6. And then 2/3, I'm going to need to multiply by 2/2 to get that same 6 denominator. So this is 3/6 plus 4/6 is 7/6. Now what we're going to be doing today is actually undoing the common denominator thing. Okay? Because the idea is, since 6 has factors 3 and 2, we're able to express 7/6 as the sum of some number of thirds and some number of halves. And that's what we're going to do, except with fractions that have algebraic things in the bottom. So basically, the bottom will need to be factorable, and then we'll split it up into distinct linear factors. And I think now would also be a good time for me to say that in the AP Calculus course, the partial fractions that we have to split apart are linear, non-repeating factors only. So that's good news for us. That means that pretty much the partial fraction decomposition that we're going to have to do is going to be mostly just a really simple case. And it seems like up to like half the time they've already factored the denominator for you. So that makes it even easier. So this should be pretty friendly to us. Another thing I need to remind you of before we go and actually start integrating with the partial fraction technique is some log rules, because this is going to be almost always on the multiple choice section of the AP exam, and we're going to end up with some logs. And of course, the multiple choices oftentimes have condensed the logs into their simplest form. So I'm not going to go into why these rules are true. If you're curious about why this is true, or you need a little reminder about this stuff, I would encourage you to go into my channel and look for a college algebra video on log properties. I'm sure there's one in there, and you can, get a more thorough explanation from that one. So the log rules that we're going to need today are that if we have the sum of two logs, we can express that as one log by multiplying the arguments. And we're going to be going that direction today. Sometimes you go the other direction, expressing the log of a product as the sum of the logs of the factors. But we'll probably be going from a sum to a product today. And then we have log of A minus log of B equal to the log of A divided by B. That one's going to be pretty common for us. And then the log of some base to some power, that's where we can swing the power around the front. So that's going to be the power times the log of the base. And that might be something, I think we would actually most likely be going that way, that direction today. But I think there will be plenty of examples for us to see how that works. Okay, before we start actually integrating these things, we need to go back over how do we break these down into their partial fractions. Now, I am assuming that you've seen this probably once before, but I'll tell you, if you haven't, if for some reason you were in pre-cal 2 years ago for y'all, or maybe, I don't know, didn't take pre-cal, or just wasn't included in your pre-calculus course, don't fear, this is not hard. Okay, what we're going to do is we're going to factor the denominator. We're going to say that I need 4 over, and I'm going to just factor this thing right now, x plus 5, x plus 1. We're going to express this as some number over x plus 5 plus some other number over x plus 1. And I usually call these A and B. Right. And now how we're going to actually find out what A and B are is we're going to multiply both sides by x plus 5 and x plus 1. So I'll get 4 is equal to A times x plus 1. Because if I multiply by x plus 5 and x plus 1, the x plus 5s would cancel and I'd be left with this x plus 1 in the numerator. Plus B times x plus 5. Again, for the second fraction, you multiply by x plus 5 and x plus 1. The x plus 1s cancel and you're left with an x plus 5 in the numerator. And then in order to kind of get A and B by themselves, I'm just going to choose the right values of x. Okay, so I'm going to let x equal negative 1. Well, if x is negative 1, then I have 4 is equal to A times 0 plus B times 4. Okay, so that looks to me like we're saying that 4b equals 4, and so that means that b equals 1. Then we can let x equal negative 5, and then 4 will be equal to A times negative 4 plus B times 0. Meaning that A times negative 4 is equal to positive 4, I think that means that A needs to equal negative 1. So, in conclusion, I'm going to say that 4 over x squared plus 6x plus 5 is going to be A over x plus 5, so that's negative 1 over x plus 5, plus B, which is 1, over x plus 1. All right, so we've decomposed that into partial fractions. Now, think to yourself, look at the original fraction, 4 over x squared plus 6x plus 5. Or you could think about that as 4 times x squared plus 6x plus 5 to the negative first power. That's not something we're going to be able to anti-differentiate very easily. Okay. Or maybe at all. Yeah, we're not, I haven't shown you all about complete the square, but we're not close enough to a square to do that and get, arc sine or something. But 1 over x plus, or negative 1 over x plus 5 and 1 over x plus 1 will be very easy to anti-differentiate. And then you start to see, okay, well, that's where the logs are going to get, the log properties are going to come in. All right. Next, this is actually the calculus problem here. This is what you're going to be seeing. And I'll just tell you, since we've already broken this into partial fractions, I'm just going to kind of use the result from the last example. But kind of the key that gives away that this is a partial fraction integration problem is the denominator being factorable and it being bigger on bottom. I'll talk about what happens if we encounter a fraction that's larger on top here in a little bit. But for here, 4 over x squared plus 6x plus 5, you're looking at this, you're saying the denominator is factorable, I need to use partial fractions. Well, based on the previous example, I can say that this integral is equal to the integral of negative 1 over x plus 5 plus 1 over x plus 1. And then we know how to take these antiderivatives. Okay, this will be the negative log of absolute value x plus 5 plus the log of the absolute value of x plus 1 plus c. Right, now, this would be a perfectly fine place to stop for y'all in a free response or a quiz type scenario. But I told y'all earlier, this is almost guaranteed to be a multiple choice question. And when that happens, it's probably not going to look like this. Probably what you're going to need to do is apply log properties. So I'm just going to kind of switch the order here. And then I'm going to apply a log property. Because I've got the difference of 2 logs, so I should be able to condense them into the log of some kind of fraction. What I'm going to do is say that's the log of x plus 1 over x plus 5 plus c. And that's most likely what your correct answer choice in a multiple choice setting would look like. Okay, now, if you're thinking to yourself, well, why just one set of absolute value bars? Think about what happens when you take the absolute value of something divided by the absolute value of something else. Is it any different from if you just took the division and then took the absolute value? I don't think it would be. I think it's just going to come back positive no matter what. All right, the next example I got for you is find the antiderivative of 8 over x squared minus 4 dx. Again, I'm seeing the denominator is factorable, so I think that means that I'm going to want to use partial fractions. All right, and I think, you know, this technique is not that demanding. I think y'all are ready to try this on your own. Give this one a shot. If you're watching at home, you can just follow along with my work. We'll have more examples that you can, you know, try on your own. I'm going to freeze the screen for those of y'all in class right now. All right, there you go. So, you know, if you're good through a and b, you got a equals -2 and b equals 2, or not really necessarily a is -2 and b equals 2, but the number that goes over x plus 2 is -2, and the number that goes over x minus 2 is positive 2. Then that's good. Okay, we need to be able to do that algebra. And then, you know, if you're having trouble with the anti-differentiation, well, there will be plenty of practice on that on the homework. And I just also want to point out that starting here, what I've underlined in green, is a safe place to stop. Okay, as far as free response, quiz, something like that. The rest of it is all just, you know, extra, making it look nice, maybe trying to make it look like the multiple choices options. Here's one that, okay, the denominator is factorable, but I'm not going to use partial fractions. Okay, this one is bigger on top. So what I need to do is do long division. Okay, so that's something I'm just going to remind you about. 1x to the third minus 2x squared plus x plus 1. And if there was some term that was missing, I would put in a 0 for that. divided by x squared minus x. So you think to yourself, what do I multiply x squared by to get to x to the third? That's x. Okay, so then I multiply it back again. I've got x to the third minus x squared minus... No, that's it. Okay, and then I subtract this, and I get negative x squared plus x plus 1. I do the same thing. What do I multiply x squared by to get negative x squared? That would be negative 1 plus x plus 1. And, okay, so then you subtract this. Wait, no. And you're left with a 1. So now you're integrating this. At this point, you would have to see if you could break apart 1 over x squared minus x into partial fractions, and I think I am going to actually do that. So now this is the integral of x minus 1 plus 1 over x squared minus x. And I'm definitely going to need a little more room, so I think I'm going to clear out the long division. And I'm going to do the algebra for the partial fraction decomposition over here on the left. So I've got 1 over x times x minus 1 equaling a over x plus b over x minus 1. And so I'll, multiply both sides by that common denominator, and I'll say 1 equals a times x minus 1 plus b times x. Okay, so when x equals 1, I get 1 equals b. Oh, that's nice. And then if I let x equal 0, I get negative 1 is equal to negative 1a, which means a is negative 1. Okay, so this is working out pretty well. So now I have the integral of x minus 1 plus, okay, a is negative 1, so negative 1 over x plus b is 1 over x minus 1. Okay, and now all of a sudden this is something we know how to take the antiderivative of. This is 1/2 x squared minus x minus log x plus log absolute value, whoops, forgot my absolute value over here, log absolute value x minus 1, and plus c. So that was a pretty good one. That one involved partial fractions and a long division. And actually, I think that's all I've got for you. The other cases of this pretty much all boil down to the same thing. I mean, I could do some definite integrals, but really the hard part is finding the antiderivative. You plug in top, plug in bottom, subtract. You don't know how to do that. Pretty much, I think if you're having trouble with this, come see me in the morning and I'll help you out with it. It's just the type of thing that once you practice, it'll become really easy. Should be one of the really friendly techniques of integration for us.